on rectangular current carrying conductor. We are having this conductor A, B, C, D. This is rectangular. This side is AB, this side is length, is small l. This is BC, breadth. Similarly, D, CD is also capital small l, and AB is length. So the breadth of this coil is B and length of this coil is A. It is kept in the magnetic field. This is North Pole and this South. So the magnetic field will be from left to right. This side will be magnetic field. And if the current is flowing in, and we take the current is flowing in clockwise direction, like this. It is moving in the clockwise direction. And this is the axis which is passing through the center of BC and AC. And this is will be the axis of rotation. Now, what will be the? We have to find the force on BC, AB, CD, and D. On the force will be given by the force on the conductor. When high current is passing, then force will be equal to, this force will be equal to I into L cross P. L is the length of the conductor, B is the magnetic field, and this force. The direction of force will be given by right hand screw. So here, if we take the F2 force for BC, if this force is F2 for BC, then this force will be equal to Fi. Here it will be small b, which is the breadth cross b. So this force F2 will be equal to I B small b, which is the breadth cross b. Now its direction will be given by the right hand screw rope, and this will be upward, and this side will be in the upward direction, which is perpendicular to BC. It will be perpendicular to the BC, this side. Now if we take the for BA, this force is, we have taken F4 force. Now the similar here we will apply the force due to the current carrying conductor whose length is B. So this force F4 will be equal to, current is same I, B cross B. Now its direction is the current is in this side. Here it is in this side, so it will be in this direction. So here the force will be in the downward direction, and it will be perpendicular to AD and downward. So these two forces, F2 and F4 forces, they are equal and opposite direction. So force F2 is equal to F24, and the direction is opposite. So F2 plus F4 will be equal to 0. It means there will be no translation motion. No translation motion. In perpendicular to the magnetic field B in y direction. So net force F2 and F4, net force will be equal to 0. So it will be not moving either upper side or lower side due to the F2 and F4. Now we will consider the force F1 which is on AB. Current is here AB. Now here angle between length and is 90. So here force F1 will be L cross B. Now here angle is 90 between L and B. L is perpendicular to this. So this will be equal to I L B sin 90, and sin 90 is equal to 1. So it will be equal to I into L into B. And direction of this force will be inward, perpendicular to length and inward. So we express this by the cross. So this force F1 will be inward and perpendicular to the length and perpendicular to the magnetic field. Now F3 force between the CD direction. Now here current is in the opposite direction. Current is in the opposite direction. Here the current is from A to B, here it is C to D. Now this force F3 force will be equal to I L cross B. Now here also L and B are perpendicular, so it will be equal to I L B sin 90, which is equal to I L B. Now direction of this force will be outward. So we give it the outward force. So for BC, if we take the BC, the force is downward inside it, and for AC, the force is so force F1 is equal to F3 in the magnitude. These two, the direction of these two forces are opposite, so there will be no motion in this. But since these two forces are opposite, but they are at a distance, so one force is in this direction, another is in this direction, and they are opposite. So what will be there? It will be a constant rotational motion, and it will rotate. So there will be a rotation on the rectangular coil, and about the center, which is the, I have shown it here. Suppose this is the PQ axis, and which is passing through the center of B, BC and AD. So it will rotate due to current passing through. So now we will find what is the torque. Now what is the torque? Torque is moment of force. Torque is moment of force. Now these two forces are equal and opposite, and they are at a distance. So there will be rotation motion. Now here we take the BC. Here force is on the inside, here force is outside. So I will give it there. This force is F1 inside, and this is outside. And this is the breadth. BC is small b, which is the breadth of this. Now what will be the area? This will be the coil, and this will be the area of coil. ABCD, this will be the area of coil. And the area vector is a vector whose direction is perpendicular to the area. So the direction of area vector will be in this direction, which is perpendicular to this rectangular frame ABCD. So this is the direction of A. This is the direction of B. Now the angle between magnetic, this is the direction of magnetic field. So angle between B and A is theta. Angle between B vector and A vector is equal to theta. This angle is theta. So this angle will be 90 minus theta. This angle is 90. So this angle will be theta. So angle BCE will be equal to theta. Once I again repeat you, this is the direction of B, this is the direction of area vector, this angle is theta. So this is 90, so this angle is 90 minus theta, this angle is 90, so this angle will be equal to theta. So angle BCE, this will be equal to angle theta, which is same as the angle between B and A. So now what will be torque will be equal to moment of force. Moment of force will be equal to, so we represent torque by tau. This is equal to force multiplied by perpendicular distance. And so it will be equal to this force multiplied by perpendicular distance. Perpendicular distance is BE. Now from triangle BCE, sin theta is equal to BE divided by BC. So BE will be equal to B sin theta. This is B small b. So sin theta is equal to B beta small b. So BE this distance BE is equal to small b sin theta. So the torque will be equal to force in IPL ILB multiplied by B. So this will be equal to IB into L into B. L into B is length into breadth, that is area. So this will be equal to I into area into B. So if there are n turns in the coil, then it will be n times. So the torque will be equal to n times, if n is the number of turns, capital N multiplied by I into A into B. Now NIB, this is magnetic moment. NIB is magnetic moment. So we can have torque is equal to M, capital M into B. And if we write in the vector direction, then this will be equal to, torque will be equal to M cross B. Because between A, M is this direction, will be in the direction of A, and P, angle is theta. So we can write M, the torque will be equal to M cross B, or torque will be equal to, this is the magnitude of torque, and this torque will rotate this coil in the, this will be moving in the direction of current, that is in the clockwise direction. So due to the torque, this coil will rotate in the clockwise direction, and the value of the torque is equal to I N into I into A in B, or we can have M into B in the magnitude, and if we give the direction, and direction of magnetic field is, torque is M cross B. So it will be perpendicular to B and A vector, and it is given by the right hand rule because it is a cross product, so it is given by the right hand. So in this way we have find the torque on a current carrying rectangular coil, and the torque will be equal to M into B or N into I into A into B. A is the area of the coil, I is the current, and N is the number of turns. So this NIA will be equal to magnetic moment. So the magnetic torque will be equal to this M into B, and torque is a vector quantity, and its direction will be governed by M cross B. So we have find a similar relation for the electrical dipole. In electrical dipole, the torque was equal to dipole moment P cross E, where P was the dipole moment and E was electrical. So now here, this case is generally in the equivalent to the dipole, where dipole is when placed in the magnetic field, then electrical field, when dipole is placed in the electrical field, then torque on the dipole will be equal to P cross E, where P is the dipole moment and E is the electric vector. So in this way we can easily find the torque on a rectangular coil which is placed in the magnetic field and current is passing through it. Then it will experience a torque, and due to the torque it will rotate. Moving coil galvanometer. Now moving coil galvanometer is based on the fact that when a rectangular coil which is current carrying placed between the magnetic field, then it will experience a torque, and the torque will depend upon the current, and torque was equal to I into A into B. For if there are n turns, so n turn is fixed, area of coil is fixed, B is fixed. So torque will depend upon, torque is proportional to the current. If current is less, torque will be less. If current is more, the torque will be more. So the torque, we are having this is the figure of galvanometer. Here we have a galvanometer. Now, what is the use of galvanometer? Galvanometer is a electromagnetic device which can detect the direction of current. In some books it is written that it doesn't measure the current. It doesn't measure the voltage. It only gives the direction of flow of current. We can convert this galvanometer in ammeter by placing a small resistance parallel to its ends, terminals, then it will behave like a ammeter. And if we place a very high resistance in series with the terminals, then that will be a voltmeter. So voltmeter and ammeter can be converted from the galvanometer. So moving coil galvanometer means here with the construction, this is a magnetic, it is horseshoe type magnet. This is not straight, this is a curved magnet. Here in between there is a very aluminum, we take the aluminum frame here. Because aluminum is a light metal, number one, and it is non-magnetic. So we will use a frame of aluminum, and on that frame we will have a coil, rectangular coil, and whose one end is connected here and another end is connected here. This will turn to the one point of the galvanometer and this will go to the second point of the. Now in between this there is a cylinder and cylinder is of the iron, soft iron. So here there is a strong magnet whose shape is horseshoe magnet, and here is a cylinder which is made up of soft iron so that maximum lines will pass through it. So what is the use of having a cylindrical cylinder here and the concave type magnet here? It is to have a field which magnetic field will be a radial magnetic field. Now how it is a magnet? So here it is a N and here it is a S. This is the cylinder. This cylinder which is of the soft iron, and this is the coil. This one end it is going upward and it will be going downward. So it will be going downward, cross, and it will go up. And current is passing through it. So now when it is placed, then here, this is the line of force. It will pass through it and this way. If it is turned here, then so the magnetic field will be always, always perpendicular to the area vector. At any position, suppose it is in this position, then the magnetic field will be like this. So it will pass through it. So magnetic field will be always passing through this end and it will be always perpendicular. So torque is maximum. So we can write that torque is equal to क्या होगा? N I A B sin theta. Now here when theta is equal to 90, so it will be maximum. Torque will be maximum. Will be equal to N I A B. It will be maximum when theta is equal to 90. So for any condition, for any position of the coil which is rotating, here it will be a radial force, magnetic field, and magnetic field will be always in this direction, and magnetic field will be always perpendicular to the area vector. Area vector will be in this side. So it will be always at 90. Suppose it is here, then area vector will be this side. So area vector and magnetic field both will be always perpendicular to each another. So the torque is maximum, and torque maximum will be equal to NIAP. So this torque will depend upon NI, A and B. Now for a particular galvanometer, number of turn is fixed. I is changing, A is fixed. So torque maximum will be proportional to I. If I is small, then torque will be small, so it will rotate small angle. So here we will have a pointer here, and this is the scale, and here is a pointer, and at the center it will be 0. It is suppose 50 here, 50 here. If the current passing through this direction, then this deflection will be here. Now this deflection will depend upon torque, and this will be proportional to I. If we increase the current, it will be more, then the angle will be more. If we reverse the direction of current, then it will move in this direction. So galvanometer is used to, this is the pointer and this is the scale. where no current is passing, there is no torque will be equal to 0 and pointer will be always at 0. Now, if the current is passing through the coil, then it will rotate. So, when this coil will rotate, now here at this end, there is a hair spring here, and here also there is a hair spring. And hair spring is made up of a special wire, and which is known as the phosphorus branch. For this, the torque per unit couple is large. So, we will use the phosphorus branch. The springs are of the phosphorus branch. So, when torque is applied, then what will happen? Then this wire, the spring will be turned. Then there will be twist in the spring. If theta is the twist, in the spring of phosphorus branch, then the torque will be equal to C into theta, where C is torque per unit of twist. So, if by passing current I, the coil rotates by angle theta, it will shown by the pointer, then the torque will be equal to C into theta. As we withdraw the current, then due to this torque will be in the opposite direction to this torque. So, when current is 0, this will act and it will turn the coil in the original position, so the pointer will show 0. If current is passed, it will be here. Then its angle is theta. Then the torque, which is against the rotation, or that is we can say that is that torque will be equal to the torque due to current, and when we are equal, then this coil will stationary and angle is theta. Then torque, which is equal to I into A into N into B, will be equal to C into theta. So here I and B constant and C is also constant. So the current is proportional to the theta. So we can measure the theta. If current, we increase the current. If we increase, I increases, then theta increases. I is equal to 0, theta is equal to 0. So when it goes, now the current for the full scale deflection means when it goes to here, this is very small current, and this current is of the order of microampere. This current is of the order of microampere. So in this way, if we pass the current through the coil, then the strength of current will be proportional to theta. So more is the current, more is the theta. But by this method, we cannot measure the magnitude of the current. We can only find the direction of current. If the direction of current is one side, then it goes there. If we reverse the direction, having the magnitude same, then it will towards this side. So in this way, we can say that galvanometer is a device which detects the direction of the current. We cannot measure the current by the galvanometer. So now we will here we can have I is equal to C divided by I is equal to C divided by A and B into theta. C is the couple or torque per unit twist of the phosphorus bunch, which are the weight of the springs. A is the area of coil, that is constant. N is the number of turns, is constant. B is the magnetic field, constant due to the magnet. So this factor is known as reduction factor, and we call it K. It is a reduction factor and we call it K. So K is equal to C bata A and B. So this reduction factor is constant because C is constant, A is constant, N is constant, P is constant. So I will be equal to K into theta. So here K is the reduction factor and K should be small or more. K should be small. When K decreases, theta increases. So lesser the value of K, then more will be deflection. Means the galvanometer will be sensitive when K is small. Now to make K small, we can increase A, N or B. Now we will not decrease is very small because when if the number of turn is more, area is more, then what will happen? The mass of this will be more. So the deflection will be less. So the moment of inertia or the mass of the coil, this frame should also be very small. Otherwise, there will be a less deflection. So we cannot have much area, much number of turns to reduce it. So we will have a moderate value, and we will use here the frame which is made of aluminum. Why we take the aluminum? Aluminum is a non-magnetic substance. It's a non-magnetic substance. And when it is rotated, what will happen? We will study later. Then ED currents are formed. If ED currents are formed and due to ED current, the pointer will stop. If it is, this frame is made up of paper, then the coil will move from theta angle from this point to this point. We will not get a constant and it will be rotating like this. So to stop this rotation, at some, suppose this is at this theta, then we will use the metallic frame which is aluminum and metallic. There will be ED current. We will explain when we will study the AC. Then due to ED current, there will be the oscillation will stop and it will be have a fixed position at angle theta, and that will depend upon the current. Now next our thing, what is the current sensitivity? Now what do you mean by the current sensitivity? Current sensitivity means the less the current, more is the deflection. So current sensitivity SI is equal to 5 bata I. So current sensitivity is the deflection. Here 5 we have taken the origin theta you take. If theta is the deflection. So deflection SI is deflection for unit current. So if the current is small and SI is more, then we will say it is more sensitive. So this SI will be equal to NAB divided by C, and which is equal to 1 by K. K is C but A and B, and it is inverse of it. So it is inversely proportional to the reduction factor. So the current sensitivity will be more if the reduction factor is small. Then second is voltage sensitivity. Voltage sensitivity SB will be equal to the deflection divided by voltage, and voltage will be equal to I into G. G is the resistance of the galvanometer coil. So I into G will be equal to V. So the voltage sensitivity of the galvanometer is deflection for 1 volt. So if the deflection is more for small voltage, then it will be a sensitive for voltage. So voltage sensitivity and current sensitivity, we can divide it. So current sensitivity is inverse of the reduction factor, and it is the deflection for a unit current, that will be SI. And similarly, voltage sensitivity of the galvanometer is the deflection here, theta, we have taken theta divided by V, and V we can add V is equal to current into G. G is the galvanometer coil resistance. G is the resistance of galvanometer coil. So the resistance of galvanometer coil, it should be small or more? It should be large. So SI will be less. So it should be less. It should not be large. So the resistance of the galvanometer coil should. So the galvanometer coil is made up of thin copper wire which are enamelated, means they are insulated. If it is not enamelated, then they will contact with it. So all the wire of the galvanometer coil, they are animated by the solution and they are used. So in this way we can have a construction of the galvanometer, the principle of the galvanometer, and the current sensitivity, voltage sensitivity, and reduction factor of the galvanometer.